Okay, section 7.1, we're talking about functions with several variables. Up until now, we've only worked with functions in two variables, x and y usually. Those are all going to be graphed in the two-dimensional space. That's why you have an x-axis and a y-axis. So now we're going to add in a third dimension, a third variable. So functions in terms of three variables would be graphed in 3D. Some of these functions would give you graphs that look like what you see here. This is from your book, page 555. So these are different examples of the types of 3D graphs that could be constructed. Now, I'm not going to expect anybody to graph these without the use of technology or even with technology, but we're going to be looking at features such as high points and low points. Those are your peaks and your valleys, your critical points, things like that. So in 7.1, we have three variables, like I mentioned. The third variable is going to be called z. Z is equivalent to your function, and that's in terms of x, y. So for this first example, you're given the function f of x, y equals given 3x plus 2y over 2x plus 3y. This would be equal to your third variable, or z. We want to compute this function at the value 1, 2, which means 1 gets placed in for the x variable, and we use 2 to replace the y variable. So f of 1, 2 will look something like this. So your output value is 7/8. This gives you an ordered triple that would lie on the graph of this function. The ordered triple with the order x, y, z assumed is going to be the ordered pair, or the ordered triple 1, 2, 7/8. So this is the three-dimensional point, the point in three-dimensional space that would lie on this function's graph. We're going to discuss the domain of the given functions. The first one is the same as the one we just discussed. So the domain of the given functions relies on the same principles that we've already learned. Whenever you're looking at a fraction, if the function contains a fraction with variables in the denominator, that denominator cannot be equal to 0. So we want to make sure that whatever quantity is in the denominator is not 0, which is what we have in this first case, example number 2. So when we're discussing the domain, we can simply say that 2x plus 3y is not equal to 0. That's going to be sufficient to answer your exercises in Connect Math. Right, that's what it's going to want you to type in. 2x plus 3y cannot equal 0. That's the denominator. Anything else is okay. So that's exactly what you're going to type in. But I'm going to talk about this just a little bit more. This would equivalently say that 3y cannot equal negative 2x. In other words, y cannot equal negative 2/3 x. So if you think of the set of points that are not allowed to exist for this particular function, that would be any point that's on this line, goes through the origin. Let's see, it's going to go down 2 and to the right 3. So if I graph this line, y equals negative 2/3 x, you're going to get something like this. And so the domain for this function f of xy is going to be any point that you can come up with, except for all the points that lie on that line. So points on this line that we've graphed are not in the domain of the f of xy function given for this example. Number 3, we have a function. We have a fraction once again. We have variables in the denominator. We have another component, though. We have this natural log. And we know from our discussion in Chapter 4 with natural logs, Section 4.2, that you cannot take the log of 0 or anything that is negative. So what that means is that we want, for our domain, we want x plus y to be greater than 0. Not equal to 0 is true, but it also can't be negative. But so that we get around all of that by saying that x plus y has to be strictly greater than 0. And in Connect Math, that's exactly what you're going to type in for your answer. I'm going to take it another step further for us, though. I'm going to say that this tells us that y has to be greater than negative x, right? So any ordered pair that makes that inequality true is going to be part of your domain. So if I look at what that graph looks like, if I graph the line y equals negative x, it's going to be a line that passes through the origin with a -1 slope, and it's going to be going like this. So whenever you're graphing inequalities, we learned in college algebra, we have to shade either above or below that line. And the region that you choose to shade is the region that contains the ordered pairs that make that inequality true. So you can test any of those ordered pairs that I've shaded there, and you'll see that they all make that inequality true. That shaded region is your domain. The shaded region is your domain. So this contains all of the points in the domain of f of xy. Okay. Example number 4, what do we have? Illinois Instruments is a company that manufactures two kinds of calculators. They make scientific calculators that cost them $10 each to produce, and business calculators that cost them $13 each to produce. Part A, if X scientific calculators and Y business calculators are produced, express the cost as a function of X and Y. So this time your cost is not just made up of one variable, it's made up of two variables, right? So you're producing two separate things, which is more realistic in life situations. So scientific calculators is your X, and each one costs you $10. So the cost to make all of your scientific calculators is 10 times X. Business calculators are $13 each times Y business calculators. So this would give you your cost function in terms of X and Y. All right, I'm just going to repeat it here at the top of the next page so we have something that we can see in front of us to answer B and C. Part B, compute the monthly total cost if 300 scientific calculators and 100 business calculators are produced. Pay attention to which one is your X and which one is your Y. So in this case, 300 is your X because X represents scientific, and 100 is your Y because Y represents your business calculators. When you substitute those two numbers into your cost function that you came up with in Part A, you work it out, you should get a monthly cost of $4,300. Part C, the company wants to increase production of scientific calculators, remember that's the X, by 40 each month from the level in Part B, but the company wants the total cost of production to remain the same. So how are we going to adjust the number of business calculators to make this happen? So once again, let me bring this down a little bit for you. We want our cost to remain the same. So your cost function needs to stay equal to $4,300. Now you are increasing the scientific calculator production level by 40, an extra 40 each month. So previously, what were you making? In Part B, it said you made 300. You want that to go up to 340, right? The cost per business calculator is the same, but we want to figure out what our production level needs to be for that to happen. That's the Y variable. So you're going to solve this equation for Y. Give you a couple of steps here. 3,400 plus 13y. So you're going to subtract the 3,400. You're going to divide then by 13, and you're going to end up with y is about, we'll call it 69.23, or how about 69 calculators? 69 business calculators. All right, so how much does that represent in terms of a reduction? Remember, in Part B, it said you wanted to make 100. This, in Part C, answer says if you want that cost to maintain the same, but you're increasing production of the first scientific calculator, you need to produce 69 business calculators per month. From 100 going down to 69, this represents a reduction of 31. So produce 31 fewer business calculators. All right, so example number 5. You have a medical supply store is making 2 kinds of gloves. Sales figures indicate that the first brand is sold for X dollars per box, the second is Y dollars per box. Demand for the first is given there, the demand for the second is given there. Part A says express the medical supply store's total monthly revenue from the sale of the gloves as a function of the prices X and Y. Pause this if you need to, reread the problem so you understand what's going on. Revenue is price times quantity, right? And so we have 2 separate components. We've got what's going on with the brand, the first brand, and then we have price and quantity for the second brand. So you're going to put those together, 2 separate components added together, and that's going to give you your total revenue function. So for the first brand, remember how the price was X dollars per box? And according to your demand function, that's your quantity that's going to be required. Quantity at that price is 300 minus 20x plus 40y. So that takes care of what's going on with your first brand. Then you have to consider what's happening with your second brand. The second brand is being sold for Y dollars per box, and at that price point, you can expect to sell your second demand function. It's given as 150 plus 10x minus 20y boxes at that price point. All right, so this is your revenue function. We will go ahead and simplify this, and then if we have any like terms to combine, we will. All right, so for like terms, I see an XY term from the first simplification, and I see an XY term from the second, and that looks to be about it for like terms. I'm going to put these in order. Let's put the x squared first, the y squared next, the xy after that. So 40 and 10 is 50, followed by the x term, 300x, followed by the y term. That takes care of everything. Part B says compute the revenue from Part A if the first brand is sold for 50 and the second brand is 35. So as you might expect, we want to let X equal how much is the price for the first brand, that's $50 per box, and Y is the price for the second brand, which is $35 per box. And substituting those numbers into your revenue function from Part A, I'm not going to write it all out, but you'll have to use your calculator. Pause this if you need to. Double check your answer that you're getting. You should get $33,250 for your total revenue. And that takes care of 7.1.